By the end of this video, you should be able to 1. Describe, explain, and apply the periodic trends that are used to rank elements by atomic size, ionization energy, and electron affinity. 2. Describe, explain, and apply the periodic trends that are used to rank ions by size. 3. Deduce the identity of an element or ion from the successive ionization energy data. There are 3 periodic properties that we will discuss. First, atomic size or radius. Second, ionization energy. And third one, electron affinity. First, let us discuss atomic size or radius. As we have discussed earlier, the atoms do not have a sharp boundary like the macroscopic objects that we see every day. In addition, they are extremely small. Because of these two reasons, it is quite complicated to measure the radius of an atom. We can only estimate the radius by measuring the distance between two atoms when they are bound together by a single bond and take half of the bond distance as the atomic radius. For example, the hydrogen molecule, in which a hydrogen atom is bonded to another hydrogen atom, can be used as a reference to measure the atomic radius of hydrogen atom. The bond distance of hydrogen-hydrogen single bond is measured as 74 picometers. And half of this distance, which is 37 picometers, can be approximated as the atomic radius of hydrogen atom. The atomic radius of the representative elements are shown below. Take a look at them and let me know if you see any trends. There are two trends that are obvious from the data. The atomic size generally decreases across a period from left to right, and it increases down the group. Now, why does that happen? In order to answer the question, we need to understand the following. First, the electrostatic force of attraction or repulsion between any two charged particles is directly proportional to the product of the charges. Once we know this, we need to clearly understand the following terms and how each of them affect the atomic radius. First, nuclear charge. Second, shielding. And third, effective nuclear charge. Nuclear charge is the number of protons present inside the nucleus. In other words, the magnitude of the positive charge inside the nucleus. As the nuclear charge increases, the force of attraction between the nucleus and the outermost electron increases and the atomic radius decreases. Second, the shielding. As the electrons inside an atom are added, there is a force of repulsion between the electrons inside the atom. This force of repulsion pushes the outermost electrons away from the nucleus, thus increasing the atomic radius. This electron-electron repulsion is called as shielding. We also need to know, while the electrons in the same shell cannot shield each other well, the inner electrons can effectively shield the outer electrons. Third, effective nuclear charge. The outermost electrons now experience two different types of forces. One, the force of attraction from the nuclear charge, which decreases the atomic radius, and second, the electron-electron repulsion, also known as shielding, which increases the atomic radius. The effective nuclear charge is the net nuclear charge experienced by the outermost electrons after the shielding. That is, Z effective is equals to Z actual minus shielding. And the effective nuclear charge is the property that correlates well with atomic radius. When you are moving across a period, you are adding electrons to the same shell, and the electrons in the same shell cannot shield each other well. So, when you move from left to right across a period, the nuclear charge increases and the shielding increases. However, because the electrons in the same shell cannot shield each other well, the shielding does not increase as much as the nuclear charge. Therefore, the effective nuclear charge increases across a period, shrinking the atom and decreasing the atomic radius. When you move down the group, both the nuclear charge and the shielding increases. However, the increase in shielding is more than that of the increase in the nuclear charge. The reason is, when we move down the group, each time we add an additional energy level to the atom, and the inner electrons effectively shield the outer electrons, therefore increasing the shielding by a greater amount. As a result, the effective nuclear charge decreases and the atoms get bigger. Since the periodic table is always given to you during a chemistry exam, you should be able to arrange a given set of atoms in the increasing or decreasing order of their atomic radius. Let us do a couple of example problems before we move on. Arrange the following atoms in the increasing order of atomic radius. We are given with beryllium, strontium, and calcium. First thing I would do is locate these three atoms on the periodic table. We have beryllium, strontium, and calcium, all of them in group number 2. We know that from the left to right hand side of the periodic table, the atomic radius decreases. And from top to bottom, the atomic radius increases. Therefore, if I have to arrange these three atoms, beryllium, calcium, and strontium, in the increasing order of the atomic radius, I would write beryllium followed by calcium followed by strontium. We have another question. Arrange the following atoms in the increasing order of atomic radius. We have potassium, gallium, calcium, rubidium, and chlorine. I will again do the same thing. First, locate these atoms on the periodic table. Potassium, gallium, calcium, rubidium, and chlorine. We know that atomic radius decreases from left to right and increases from the top to bottom. So overall, the atomic radius increases in that direction. We have larger atoms in the bottom left corner and small atoms in the top right corner. So, if I have to arrange these atoms in the increasing order, I start with chlorine, followed by gallium, followed by calcium, followed by potassium, followed by rubidium. Now let us see what happens to the atomic radius when you add or remove an electron from a neutral atom. This question can be answered using the same equation, that is, Z effective is equals to Z actual minus shielding. When you add or remove an electron from an atom, the Z actual, that is actual nuclear charge or the number of protons inside the nucleus, does not change. However, the addition or removal of an electron changes the electron-electron repulsion, therefore the shielding. When an electron is removed from an atom, the shielding decreases, therefore the effective nuclear charge increases and the electron cloud moves towards the nucleus and the size decreases. Therefore, we can say that the cations are smaller than the respective parent atoms. Similarly, when you add an electron, it increases the shielding and decreases effective nuclear charge. The electron cloud moves away from the nucleus and the size increases. Therefore, we can say that the anions are larger than their parent atoms. A type of question that you may be asked in the exam is, we give you an isoelectronic series and ask you to arrange the atoms in the series in increasing or decreasing order of their atomic radius. An isoelectronic series is a series of ions or atoms that have same number of electrons. For example, oxygen 2 minus, fluorine minus, neon, sodium plus, magnesium 2 plus, and aluminum 3 plus. All these have same number of electrons, that is 10 electrons. Let's say we need to arrange them in the decreasing order of their atomic radius. As the name suggests, isoelectronic means same number of electrons, therefore same shielding. However, their actual nuclear charge increases from oxygen to aluminum. Therefore, the greater the actual nuclear charge, the greater is the effective nuclear charge and the smaller is the atomic or ionic size. If we arrange these ions or atoms in the decreasing order of atomic radius, we get oxygen 2 minus greater than F minus greater than neon, followed by Na plus, Mg2 plus, and Al3 plus. Let us do an example problem. Which of the following has largest and smallest size? We have magnesium, magnesium 2 plus ion, aluminum, and aluminum 3 plus ions. First thing I would do is locate the atoms on the periodic table. We have magnesium in group 2 and aluminum in group 3. And we know that across a period from left to right, the atomic radius decreases. Therefore, we can write the relation between magnesium and aluminum as magnesium greater than aluminum. Now, what is the relation between magnesium 2 plus and magnesium? We know that the cations are smaller than that of the parent atoms. We can write magnesium greater than Mg2 plus. Similarly, aluminum greater than aluminum 3 plus. We also know that magnesium 2 plus and aluminum 3 plus are isoelectronic with each other. That means both of them have same number of electrons. When you are comparing an isoelectronic series, the ion or atom with greater nuclear charge will be smaller in size. The nuclear charge of aluminum is 13 and the nuclear charge of magnesium is 12. Therefore, we can say that magnesium ion with a smaller nuclear charge will be larger in size than that of aluminum 3+ with greater nuclear charge. So overall, we can write atomic radius of magnesium is greater than that of aluminum, and the radius of aluminum is greater than the radius of aluminum 3+. Magnesium 2+ is larger than aluminum 3+ and smaller than magnesium. So it falls somewhere in the middle of magnesium and aluminum 3+. So we can say that magnesium is the largest species and aluminum 3+ is the smallest species. The second periodic property, ionization energy. Ionization energy is the energy required to remove an electron from a gaseous atom or ion. It is usually expressed in the units of kilojoules per mole. The equation to represent ionization energy is the following. Beryllium atom in gas phase loses an electron and forms beryllium plus ion in the gas phase. The change in energy for this reaction, that is delta E, is equal to energy of products minus energy of reactants. This change in energy is ionization energy. And for beryllium, it is 900 kilojoules per mole. The general trends in ionization energy are opposite to that of atomic radius. When you move across a period from left to right, the ionization energy increases. As we have seen in the atomic radius, when you move left to right in a period, the nuclear charge increases and the shielding increases. However, because the electrons are being added to the same energy level, they don't shield each other well. That is, shielding doesn't increase as much. Therefore, the effective nuclear charge increases, electrons move closer to the nucleus, and it requires more energy to remove the electron out. When we move down a group, the ionization energy decreases. The reason is the electrons that are being removed are coming from a higher energy level. As n increases, the size of the orbital increases and the electron is easier to remove. There are a couple of exceptions to the general trend in the ionization energy across a period. When we move from group 2A to 3A, the ionization energy decreases as opposed to an increase. We will take the first elements in both the groups to give an explanation for this. When you go from beryllium to boron, the electron enters into a p orbital. Since the s electrons are more penetrating than p electrons, that is, on an average, s electrons spend more time closer to the nucleus than p electrons, the s electrons can shield the p electrons better. Therefore, the outermost electron moves away from the nucleus and it's easier or takes less energy to remove the electron. Second exception. When you move from group 5A to 6A, the ionization energy decreases as opposed to an increase. In nitrogen, we have a half-filled p sublevel, that is, one electron in each of the p orbitals. When we move to oxygen, an extra electron is added to oxygen. That is, one of the p orbitals is now fully occupied. The electron-electron repulsions in the fully occupied p orbital increases shielding and makes it easier to remove either of these electrons. Now we will discuss higher ionization energies. Let us start with beryllium atom and remove one electron from it. The energy required to remove this electron is called ionization energy, and for beryllium it is equal to 0.90 megajoules per mole. This process produces a beryllium plus cation. We can take the beryllium plus cation and ionize it further, that is, remove another electron from it to produce beryllium 2 plus. This energy is called as second ionization energy. As we are removing the second electron out of the beryllium atom. If we go back, the energy required to remove the first electron is usually referred to as first ionization energy or ionization energy. We can continue this process and remove another electron from beryllium 2 plus to produce beryllium 3 plus ion. The energy required is called as third ionization energy, and so on. The general trend for any atom is that the ionization energy 1 is smaller than ionization energy 2 is smaller than IE3, and so on. The reason is every electron that is removed decreases the shielding, increases the effective nuclear charge, and the outermost electron moves closer to the nucleus, and it will be that much difficult to remove the next electron. However, for beryllium, the increase in ionization energy from IE2 to IE3 is much greater than the increase in energy from IE1 to IE2. That is, the third electron in beryllium is much harder to remove than that of the second electron in beryllium. Why is that so? The reason for this is the first two electrons in beryllium comes from the valence shell or outermost shell, and for beryllium it is n is equals to 2 level. But the third electron comes from the inner shell, that is n is equals to 1 shell, which is much closer to the nucleus. Therefore, there is a big increase in the ionization energy when the removal of electrons transitions from the valence shell into the inner shell. The successive ionization energy values of a given atom can tell us how many valence electrons are present in that atom. For example, how many valence electrons are present in a hypothetical atom for which the successive ionization energies are the following. Ionization energy 1, 1000 kilojoules per mole. IE2 is 1900. IE3 is 3100. IE4 is 5020. And IE5 is 19,000. Since there is a big jump in the energy required between IE4 and IE5, we can say that the fifth electron should come from the inner shell, and the atom should have 4 electrons in the outermost shell or the valence shell. Let us do another example problem. explain why sulfur has smaller ionization energy than expected. Let us first locate sulfur on the periodic table. It is in group 6 and period 3. Ionization energy across a period from left to right, it increases. However, the ionization energy of sulfur is lower than that of ionization energy of phosphorus. Anytime we see a break in the trend, it is helpful to look at the electronic configuration to explain why there is a break. The electronic configuration of sulfur is neon followed by 3s2 and 3p4. If I draw the orbital diagram, it would be 3s2 followed by 3p4. Usually, there are two possible explanations for this. One, the last electron entering into the sulfur atom increases the electron-electron repulsion in the p orbital. Therefore, the shielding increases and it becomes easier to remove either one of these electrons. The second explanation for the break in the trend is the following. When you remove one electron from sulfur, it will produce a half-filled p subshell. These half-filled p sublevels are unusually stable. Because removing one electron from sulfur atom leads to this half-filled p sublevel configuration, which is unusually stable, it requires less energy than required to remove that particular electron. The next periodic property is electron affinity. Electron affinity is the energy change that occurs when an electron is added to a gaseous atom. It is again measured in kilojoules per mole. For example, if we take an atom X in its gaseous state and add an electron to it, that is, X gas plus electron gives X minus ion in the gas phase, the delta E is equal to the energy of products minus energy of reactants. This is equal to electron affinity. In other words, electron affinity represents the likelihood of a neutral atom to gain an electron. So, what do you think this energy change will be? That is the energy released or absorbed? When you remove an electron from an atom, we break a bond or electrostatic force of attraction between the nucleus and the electron. So, it requires energy. On the other hand, when you add an electron, we create a bond or an electrostatic force of attraction between the nucleus and electron. Therefore, electron affinity in most cases is a negative number. That is, the energy is released in the process. More negative the energy is, the greater is the quantity of energy released and the greater is the likelihood of the atom to accept an electron. The figure below shows electron affinities in kilojoules per mole for various representative elements. For example, group 17 elements, that is halogens, have a very high electron affinity. That is, these atoms are more likely to accept an electron and form anions. On the other hand, noble gases have large positive electron affinities. What does that mean? When you add an electron to any of these atoms, energy is required. That is, they are unlikely to gain an electron. The reason for this is the electron that is being added has to enter into the next higher principal quantum level, making the atom very unstable. The trends in the electron affinity are not as systematic as the trends in atomic radius and ionization energy. Across a period from left to right, the effective nuclear charge increases and it attracts the added electron more strongly. Therefore, the likelihood of an atom to gain an electron increases and the electron affinity values become more negative. Even though this is the general trend, there are several exceptions that can be explained considering how the electron-electron repulsions change as a function of electron configuration. For example, the electron affinity of nitrogen is supposed to be a higher negative value than that of carbon. However, it is a positive number. That is, nitrogen is unlikely to accept an electron. Why do you think nitrogen is unlikely to gain an electron? The answer to these kind of questions lies in its electronic configuration. The electronic configuration of nitrogen is 1s2, 2s2 and 2p3. All the p orbitals are half-filled. The added electron has to go into one of these half-filled orbitals, which increases the electron-electron repulsion and makes the nitrogen unstable. Therefore, it is unlikely to gain an electron for nitrogen. Down the group, the effective nuclear charge decreases and the outermost electron level gets farther and farther away from the nucleus. Therefore, the nucleus attracts the added electrons less strongly. That is, the electron affinity should become less negative. This trend is only observed in group 1 elements, and all the other groups have several exceptions to these trends.